Hi student, this script is the demonstration of an example to determine the absolute maximum shear force on the 15-meter long simply support beam, and also to determine the absolute maximum moment on the beam. And what we are going to compute here is based on the chapter 6 of influence line of statically determinate beam. When we talking about determining the absolute maximum shear force on the simply supported beam, what we should know that most of the time the absolute maximum shear have some specific location to occur. For example, if we have this simple beam and it's subjected to a given 10 kilonewton force, that is maybe 1 meter here and 2 meter here, and you guys have the pin support here. Let's say this is the AA sub y and this is gonna be the A sub x, and you guys also have this one for the B sub y. For this case, we can determine the shear diagram of this beam to be like this. What does it mean this? If you do this, you may see the shear force, the Vmax, is gonna occur at the support of the beam. So the first one, when we start to determine the absolute maximum shear force, we should know that the absolute maximum shear force, VABS maximum, is occur at the support of the beam. It won't occur in the middle span of the beam. It will occur at the support of the beam. And to find it, we're gonna draw the influence line of reaction to find the loading pattern of the moving load, this moving load here. So we have the moving load here. We're gonna draw the influence line of the reaction first and determine the loading pattern of the moving load. That is going to be the learning objective 1 and learning objective 2 of this study. And if you determine a proper moving load, we will get the maximum shear. That means we're going to do the time and error by moving load appropriately to our beam. For the first one, let's have the 15 meter long. So let's make the scale of this to be we have this for 7.5 centimeter. If that's going to be, that is going to be 2 meter for 1 centimeter. So that means we're going to have this beam for 7.5 centimeter. And we're going to put the moving load onto this beam. And if you do that, you may have putting the moving load like this. This is going to be 125 kilonewton and this is 2 meter. 2 meter is 1 centimeter, so it's gonna be this one. And next is 3 meter. That is gonna be 1, 2, and 3. And then you got the loading on this beam, and you draw it on scale. So the loading gonna put into this beam like this, and you will consider the case that's going to produce the maximum shear force, and since it occur at the support, it's going to be the absolute maximum shear force. Okay, next we draw the inference line of reaction. Okay, and most of the time, since the load can move freely, so the absolute maximum may occur at A or at B. Okay, and the value going to be the same. Okay, by doing that, let us just draw the inference line of A sub y. Inference line of A sub y, and if you like, you may draw the inference line of B sub y and do the same thing. You're going to get the same result. This is going to be the roller. The roller cannot move vertically. It's only allow rotation, right? And the pin, okay, the pin, we're going to use the Musler-Best law. If we use the Musler-Best law, we will allow the A gonna move in the vertical direction. However, since it is a pin, okay, there's still the resistance on the x direction. Okay, and then you put the A sub y to push this one up, release the resistance to A sub y, and put the A sub y to move this one up for 1.0 unit. Okay, and then it's going to be here 1 centimeter, and the shape of this beam for the rigid beam is going to be in the form like this, and this is going to be the shape of the inference line of A sub y also. Now you have a series of point load that acts on this beam, and you know that to determine the maximum shear force, you will put the force into cases. Okay, by doing this, let us start by putting 3 forces on the beam. This one may be the pattern, that's the moving load, the car moving to Bangkok. Okay, and then if you reverse this, it may moving back to Korat. Okay, if we may consider another one, the loading pattern of this beam that may happen in the form like this. That is going to Bangkok, and then you reverse this. This is pin, this is the roller. Okay, and you have this is going to be 50 kilonewton. You reverse this. This is going to be 50 kilonewton. This is 2 meter. This is 3 meter. So it's going to 3 meter. That is going to be 1.5 centimeter by our scale. This is going to be 3 meter, and this is going to be 2 meter, and then 50 reverses. This is going to be 100 kilonewton. This is 100 kilonewton, and this one going to be 125. Okay, and let us compare these two cases first. Okay, for the case 1. For the case 1, we have this portion. So we can determine this A sub y. As I mentioned, the V and the A sub y gonna be the same. Okay, this V max and the A sub y will be the same. So that's why we draw the inference line of A sub y. So this case will be what? This case gonna be this 125 times this, and this one gonna times this, and this one gonna times this. Okay, I call this one is y2, and this one gonna be y3, and we can determine y2 and y3 by similar triangle. So 125 times 125 times 1. Okay, that's gonna be what? 125 times 1. And next, what we have is the coordinate of this. We're going to have what? y2 is here. y2 is here. And this is 2 meter. The total of this is 15 meter, right? So minus this one is going to be 13. So we have the y2 divided by this length 13. That's going to equal to, this one is 1 divided by the total length of 15. So we have y2 equal to 13 divided by 15. Okay, so next we have plus 100 times 13 divided by 15. Okay, and the last one is here. This is 2 meter, this is 3 meter, and this length gonna be 10 meter. 15 minus 5. So we have y3 divided by 15. 10, sorry, equal to 1 divided by 15. So we get y3 equal to 10 over 15. So next one, plus the 50 times what? 10 over 15. Okay, and finally, if you do the calculation, you may pause this and do the calculation, you will get the result here of 245 kilonewton. That is for the case 1. Okay, the car moved to Bangkok, and then the car moved back to Kolat, case 2. Case 2. Okay, it should know that this one always positive, right? Okay, this one gonna be a sub y equal to, this time 50 will times 1. So we have 50 times 1 here. Okay, 50 times 1 here. And then what we have is what? What we have is the 100. Okay, gonna project up here. Okay, and this one we may have y4. And this is 3 meter. The total is 15. So this distance gonna be 15 minus 3. That's gonna be 12. So it's gonna be y4 over 12 equal to 1 over 15. So you get this one of what? y4 equal to 12 over 15. Okay, next one. We go to plus. This time it's 100. Okay, and then the coordinate here is 12 over 15. Okay, and the last one, last one you got this one for 125. This one is 125, and it's going to be in the same, actually it's supposed to be the same here because it's 5 meter. Okay, this is 5 meter, so this one's supposed to be here. So it's going to be 125 times what? Times this one, times 10 over 15. And then you get the a sub y of this time of 13.3 kilonewton. That's pretty close, but less than the first case. Okay. And next, we consider in the case that there is only 2 loads that put on the beam. For example, this one is here, and 100 move to here, and 500 move to here. So for the next one, we may have this beam. This is the pin this is the roller, and we have only 2, so we put the 100 kilonewton here. That's 100 kilonewton. And 3 meter, 1, 2, and 3. And that's going to be 50 kilonewton. And then between this is 2 meter. So it's going to be 2 meter, and put the 125 kilonewton out. Okay, this is going to be this case bus, the 125 kilonewton out of the beam. And the last one is here. But this time is related to this one. What we have is what? What we have is we're going to move this one out. Okay, so it's going to have 100 kilonewton, 2 meter, 125 kilonewton. So we're going to have 100 kilonewton here and 2 meter. This 2 meter is here. That's going to be 125. This is 125 kilonewton, and this is going to be 2 meter. And then another 3 meter, that's going to be 1, 2, and 3. And this is going to be the 50 kilonewton. Out there, that's going to be 3 meter. Okay, if you can see, the first one is 100 times 1, the same. And this one, 125 times this. This one is 50 times this. So this one going to produce less shear force. Okay, we will consider only this. Only this. So case T, we have this case, and our A sub y gonna be 50 times 0. This time 50 times 0. And then the 100 gonna times 1. And then 125 plus 125. 125 we gonna project is up, okay, and it's only 2 meter different. So the value of this gonna be 13 divided by 50. Okay, so that's one going to time the 13 divided by the 15. And then you get this last one of 208.3 kilonewton. Now you arrive at the solution. Okay, thus we have the V absolute max equal to this one, kilonewton. We got what? We got 245 kilonewton for this. And the answer is going to be 245 kilonewton. Okay? And that is the first one. You guys need to be very careful when consider the cases that will produce the maximum shear on the beam. And next, we're going to compute the absolute maximum bending moment. For the simple beam, the shear occurs at the support. The maximum moment occurs near the midspan of the beam. Okay, so let us start by this is going to be the second. We determine the absolute maximum bending moment. Okay, by doing this, we have a set of moving load, and we will have step. The first one determine the resultant of this load. Okay, the second one, you may determine the position of that resultant force with respect to a reference line. Okay, and also if you like, you can divide that X bar and mark that position to put into the first case, and then we can consider the second case later. Okay, anyway, let me start by considering this, the first one, 2.1. okay, we find what? We find F sub R. Okay, and then the F sub R is gonna be 125 plus 100 and plus 50. You will get this easily to 275 kilonewton. Okay, since this one is too small, let me put it a bigger scale as we have it before. This is 2 centimeter, sorry, 1 centimeter for 2 meter. So this is 3, and this is 1, 2, and 3. So we will have this for 125 kilonewton, and this one for 100 kilonewton, and this one, small one, is going to be 50 kilonewton. And this F bar supposed to be somewhere here. Okay, it's going to be somewhere in the maximum force. And let me put this as the reference line and mark this as the X bar. Okay, so by using the concept of equivalent of moment, okay, by 2.2, by using the concept of equivalent of moment, okay, we will have summation of moment due to forces or loading equal to F sub R times X bar, or equal to the moment of the resultant force. Okay, so this one gonna be F sub R, and we have it for 275 kilonewton. And by doing this, what we have is the 225 times X bar, and it's gonna equal to, okay, this is the reference one, so 125 times 0. Okay, and the concept of equivalent moment gonna rotate in the same direction is equivalent of moment gonna rotate in the same direction. So this one, we compare only magnitude, it's gonna be clockwise, and this one gonna be clockwise due to the equivalent of moment. So the 100 gonna time plus 100 time what? The distance here is 2 meters. Okay, and plus this one is 50 gonna time what? This is 2 meters, this is 3 meters, that is gonna time 5. And you put them into your calculator, you're gonna have X bar equal to 0, 200, 250, that is 450, divided by 275. Okay, and then you get the X bar of 1.636 meter. That is going to be the X bar. Okay, and what we have is this 1.636. This one is going to be 1.636 meter. Let me focus on this moving. Okay, this going to be, you're going to separate this beam into two parts. Okay, each of them gonna be this x bar divided by 2. Okay, that means this is gonna be the distance of what, of x bar divided by 2, half of that. Okay, that is gonna be 0.818 meter. And if you mark this with the blue line, we will put this blue line to the middle of the beam for the first case, and we will determine the maximum moment of that case. Okay, and then you also, if you minus this 2 meter by this, you will get this distance of 2 minus 1.636. What you get for that is going to be 2 minus 1.636. It will be 0.364. This is going to be equal to 0.364. And then you also need to divide this portion into half. Okay, and you may put this blue line over here, and we also will put this light blue line into the midspan of the beam later. And what we have here is half of point this, and this half of 0.364. That is going to be 0.182. Okay, this is going to be 0.182 meter. Okay, that is the point that we gonna focus on this moving load. And for that, we're going to consider the case 1. Okay, let us consider the case 1. For the case 1, let us draw the beam again. And then we have the pin here, we have the roller here, and we're gonna divide the beam into half. Simplify is about this point, and we have this. Okay, for the first case, we will put the blue line. Put the blue line here. Okay, when you put the blue line here, that means you're gonna measure 0.818 to the left. So we put 0.818 to the left. That is going to be very small. It's going to be very small. Let me put this one here. And what we have is, this one is 125 kilonewton. So just put 125 kilonewton here. And then you measure 2 meter. That is 1 centimeter here. You get 100 kilonewton. That is 100 kilonewton. This is 2 meter. And then another 3 meter. 1, 2, and 3. You get this one for 50 kilonewton. Okay, and you also has the F sub R. You put the F sub R here. This is going to be F sub R. And the distance here is going to show here of 0.1, the 0.818 meter. And what we have is this beam separate into half. by the midspan here. This is going to be 7.5 meter, and this also 7.5 meter. And the concept is the maximum moment gonna occur, okay, under the load that is close to the F sub R, okay, in between, okay. And for this one, I will try to prove, to check the maximum moment gonna occur under this one or under this one, okay. And we will arrive at some important conclusion later, okay. By doing that, let me draw the free body diagram of this part of the beam, and also draw the free body diagram of this part of the beam, and let us calculate the bending moment occur under this 125 kilonewton, and this one for 100 kilonewton, okay. And then what we have here is going to be this distance is what? This distance is going to be this one, this 0.364, okay. And if you consider this one will have the what, this is a B, this is a A, this is going to be the B sub Y. We're going to have the reaction B sub Y here, and we also have the reaction A sub Y here, and A sub Y going to apply on this portion of the beam, okay. And what we have is, how long is this one, okay. If you consider this, we're going to determine the bending moment over here that we have. This one is M pam pam, and also for this one we will determine the moment to compare with that. Let's see, this one is going to be the M pam. Don't forget, we also have the shear, and most of the time we left without drawing it to, because it's going to messing up, okay. But showing here is really nice. And what we have now is what is this distance. This distance gonna be what, 7.5, okay. And then minus this of 0.818, and then minus this for 0.364. So this one gonna be 7.5 minus 0.818 and minus 0.364, okay. And then you have this for 6.318 meter. Body portion, this is 7.5 meter, and this is 0.818. So the distance here is 7.5 minus 7.818, and then we have this of 6.682 meter. Okay, now we have all required free body diagram, and we're going to determine the reaction, and when we get the reaction we can determine the M palm and M pam pam, okay. And let's try to zoom it out a little bit and move it like this, okay. So next step, we're going to have the 2.3, okay. Consider the case, let's see, A. Case A. I call this one is case A, okay. And what we have is, by using the free body diagram of the beam. Okay, we have what we have. If you like to determine the a sub y, just take summation of moment of b equal to 0, and then the a sub y gonna rotate this one plus, and what we have is the a sub y gonna time the a sub y gonna time the 15, so we have 15, and then a sub y equal to, so there is a choice. If you like to have the hard choice, you may determine the moment by using this 50 kilonewton, this 100 kilonewton, and this 125 kilonewton about B. Okay, and if you like the easy way, you may use the F sub R times the distance here. Okay, it's going to be the equivalent of moment. It's going to be based on the equivalent of moment. Okay, if you guys know that the concept of equivalent of moment is going to help you to do this calculation. Okay, I am using the equivalent of moment, so the 275 is my F sub R. Gonna time what? Gonna time this distance. This distance going to be 7.5. Okay, and minus this, so it's going to be 7.5 minus 0.818. Okay, and then if you do this, you're going to get the a sub y, and you may get a sub y equal to, I'm putting this because we don't have much space to write. 122.5 kilonewton. Okay, and this is going to be 122.5 kilonewton. And then we're going to find f sub b also. Summation of f sub y equal to 0, and then upward is positive. So we have the b sub y here, and plus a sub y 122.5. Okay, and this one gonna equal to, you have a choice. You may use the resultant force, and you cannot use both. Okay, that is going to be 275. We're going to have the b sub y equal to 152.5 kilonewton. Okay, and we have this one is 152.5 kilonewton. Normally we didn't do this. Okay, guys, we do this because we like to check, okay, the concept, which point going to produce the maximum moment for this case A. Okay, then by using the free body diagram of the beam's segment, we have two segments. We have S here. Okay, the first one is up to you, which one you like. Let us try to find the M palm first. Let us find M palm first. So we take the moment, summation of moment equal to 0 about this. Okay, about this, and what we have is going to rotate counterclockwise, so the counterclockwise rotates is positive. And what we have here is M palm is here. This one produce no moment, the shear also, okay, is going to equal to 122.5. This one gonna rotate 122.5, and it's gonna time this distance, gonna time 6.682, and then you get M palm easily. Just put into your calculator, pause the video, you will get this one for 818.5 kilonewton meter. Okay. This is going to be 818.5. And then you have another one here. You may take this summation of moment equal to 0. This time positive moment clockwise. So M pum pum. Oh, and forget we're going to have this one also. This is 50 kilonewton and 3 meter from here. M pum pum gonna be what? M pum pum rotate here. So this one rotate in opposite. So equal to 152.5 and time what? Time 6.318 times 6.318. And you also have this 50 kilonewton rotate in the same direction as N pum pum. So it's going to be minus. You mark in the opposite of the equal sign, 50. And it's going to time 3. Okay, you get M pum pum this time. It's going to be 813.5. Is smaller. Okay, it's this smaller kilonewton meter. A little bit smaller, 813.5. So we arrive with something. The general word said the maximum will occur under the force. Okay, that's near the F sub R. And now we arrive at a conclusion that the maximum M, okay, is occur actually is occur under the load, under the load or the force that is near what? Near the dashed pink line. Okay, near the one that's close to this midspan, actually midspan of the beam. Okay, it's going to be our conclusion. So for the next one, we may use this conclusion. The next one, let me put the beam as before, and we have this at 1, 2, 3, T.5 about this point. Okay, and we're going to have the blue line, the blue line. We'll put the blue line here. Just put the blue line from here to here. Okay, and this time, if we do a small zooming, you may see that we will measure, okay, 0.182 to the right, and then we get 100 kilonewton. Okay, okay, let me put this one very small, and then we arrive at 100 kilonewton. This is going to be 100 kilonewton. And then if you draw it 3 meter, that's it's going to be 1, 2, and 3. You get 50 kilonewton. And if you to the left for 2 meter, that is 1 centimeter, you have 125 kilonewton. Okay, and between this half, you get this one for the F sub R. This is going to be F sub R, and the distance of here, you already know that is 0.8182. Okay, this is going to be 0.182 meter. And you also know that the distance here gonna be the x bar. Okay, the x bar is 1.636. This is 1.636 meter. And what we have now is the beam for the second case gonna be something like this. And this is gonna be 7.5 meter apart for the light blue line. Okay, this is 7.5 meter. This is 7.5. And by this conclusion, as before, we are sure the maximum moment for this case gonna occur under the load that's close to the midspan of the beam. Okay, so our beam, our portion of the beam or the beam segment that we are going to use this one, and this one gonna be the B sub y, and this is gonna be the B sub y. And we have what? We have 100 kilonewton here. This is 100 kilonewton, and this is gonna be 50 kilonewton, and this is 3 meter. Okay, so what the length of this segment here to here is 7.5, and this one is 0.182, so it's going to be 7.5 minus 0.182, and then you may get this of 7.318 meter. Okay, and now we're going to determine the moment here. It's going to be m pum. Okay, first you use the free body diagram of the beam. Again, we use the summation of moment. This time we take the moment about A, because we like to find the B sub y, A equal to 0. Then the rotation of this is going to be positive, and it's going to be what? 15 times B sub y, 15 times B sub y, and it's going to equal to this one, F sub r, so 275, gonna time this distance measure from the F sub r to point A. So this is 7.5, and this is going to be 0.182, so it's going to be 7.5 minus 0.182, and you may see this is going to be the same as this one, and it's going to be equal to 7.318. Okay, that is going to be 7.318, and then we get the B sub y. B sub y equal to what? 134.16 kilonewton. We get this. Okay, and also 124.16 kilonewton here. Now we're going to find the moment here. Just the summation of moment equal to 0. This time is plus. Okay, we have m pum, m kit pum. Okay, and it's going to be plus take one here, plus 50 times 3, and it's gonna equal to 134.16. Gonna time this, gonna time 7.318. Okay, and then if you do like this, you will get the answer of this beam. And what do you get from this? You may get the M palm equal to 831.9 kilonewton meter, and you may conclude that, okay, by having the maximum of 818.5 at this one, so we get thus M absolute maximum gonna be equal to 831.9 kilonewton meter. That is the answer to this problem, okay, and that is going to be the absolute maximum moment for this beam. Okay, that is the end of this example. I think you can do it, okay, and for the absolute maximum shear, you got to do the trial and error by some logical thinking, okay. For the maximum moment, we are two cases, okay, the pink and the light blue. We also found that this one, the light blue, gonna produce the absolute maximum moment. And we also find that comparing for these two loading, the one that's close to the middle span gonna produce the maximum moment, okay. The M palm is larger than the M pam. So we can apply this concept. This one is close to the center than the 125, so we arrive at the absolute maximum bending moment as we have. Okay, let me end this example here.